All right, gang, Math 5500. Going to be a lot going on in this video, and I've been trying to keep my videos at 20 minutes because research shows that that's the most effective, well, 20 minutes or less. Well, I don't know. I don't think a video of 2 seconds would be very, but anyway, around 20 minutes. So I'll try to keep it at that, and if I'd quit talking about useless stuff, maybe we would get that done. All right, and, I don't know why I am all of a sudden writing like up. Uh, I told you, I think previously that studies have been done that shows that that's just evidence of extreme confidence or something, which, whatever. Okay, anyway, what we're going to get accomplished, hopefully, in this video, if I'd quit talking and get on task, we're going to use the dataset ACT district, so if you want to go ahead and locate that in the dataset folder in Blackboard. We're going to look at dummy variables, T-test for estimates, and the F-test for the regression relation. And I'm going to do it in this order. This is going to be first, this second, and this third. All right, so, but the primary focus here, I think, is review, and then teach new stuff in terms of the dummy variable. Now, what I want you to know on let's say, for example, that we are predicting first-year college GPA from, of course, a beta 0, and let's say, a beta 1, which is, the coefficient for maybe ACT, and a beta 2, which is a coefficient for high school GPA, whatever. Just a few predictors here. From the coefficient estimate perspective of the t-test, what we conduct is we conduct multiple t-tests. So the first thing I would conduct is the beta 0 equal to 0 versus h sub a beta 0 not equal to 0. Now, if you've been paying attention, you know that I don't find this testing the significance of the intercept to be that interesting. But nevertheless, it is tested in the R output. The other thing in this situation, we would test that the slope of of ACT is not equal to 0. And similarly for the high school GPA. So the t-test for the estimates of the regression coefficients conducts 3 separate t-tests. And we see them on the line. We see the estimate, then we see the standard error, then we see the test statistic, and then we see the p-value. All of this is created from its own test statistic, which will be the estimate minus the hypothesized value over the standard error for the estimate. And I'm not going to run through each of these because it's pretty self-explanatory, at least from the background that we have now. The estimate is just the coefficient that we get from the R output. That's just multiple ways to find that, and then the standard error for that particular coefficient would be found using the variance-covariance structure for B, which we've studied pretty much ad nauseum. Now, let's move into ANOVA. All right, so what's really going on in ANOVA in the context of this example? Well, here we have the assumption that both of our predictors, the slopes, are equal to 0. So we're not looking at it in terms of the coefficient diagnostic or coefficient test. We're looking at it in terms of a model diagnostic. Are both of these things equal to 0? our H sub A would be that either or both are not equal to 0. So again, the ANOVA is a model diagnostic. It assesses the fit of the model, not separately through the t-test. Now, what's the ANOVA, and I'm just kind of setting up the stage here, what does the ANOVA table look like once we introduce multiple predictors? Well, in the classic case, we still have our source, which is still going to be the regression, the error, and the total. We still have our sum of squares, which is easy to find. For example, we've seen previously that the sum of squares for the error is y transpose y minus beta transpose x transpose y. Okay, and we've seen that the sum of squares for the regression, the sum of squares for the total is just y transpose y minus 1 over n y transpose jy. And of course we've seen the regression as well. So now we get into the degrees of freedom. The degrees of freedom turn out to be if we let k equal the number of predictors. Now, I think this is the easiest way to remember the degrees of freedom for the ANOVA table. Now, not including beta 0. Beta 0 is not really a predictor. Our degrees of freedom for the regression term just turns out to be k, the number of predictors. The error term turns out to be n minus k minus 1, and the total just turns out to be, as it was before, n minus 1. So you can see that when we add the degrees of freedom for the regression and the error terms, we get n minus k minus 1 plus k, which gives us n minus 1. Then the mean square development is exactly the same. It's the sum of squares regression divided by k, and the error term, of course, is the sum of squares error divided by n minus k minus 1. Typically don't look at the mean square for the total because these aren't additive. Then we get our F statistic, which of course is the ratio of these two values, and we can calculate our p-value accordingly. So what we're actually looking at here is we're looking at the F distribution with degrees of freedom k, n minus k minus 1. Now, in a simple linear regression case, how many predictors do we have? Well, we have 1, and that's why we put a 1 for the degrees of freedom of the regression. So, all this stuff has been covered previously. I just wanted to wrap up a few things. Sometimes when I finish a video, it'll hit me. I wish I'd gone into a little bit more depth on a couple of things, and sometimes I'll just scrap the video and create a new one, and then sometimes in the next video, because guys, you expect to come to class every day, all right? So, and that the equivalent of coming to class every day is watching the instructional videos. I think that about nails what I wanted to do here. So let's dive into. I feel like I'm forgetting something, but I just don't know what it would be. Okay, well let's escape this and get out and go to the illustration of dummy variables. Now, one thing I do want to, let me bring this back. All right, for dummy variables, and please forgive me for the simple nature, simple level for this illustration, but when I'm teaching like y equals mx plus b to my maybe my intro developmental math courses, or maybe an Algebra 1 class, whatever. It's been forever since I've taught anything at that level. What I do to try to motivate the interpretation of the m and the b, which we all know is the slope and intercept respectively, is I give one of these one of these very meaningful tables. And I say, well, what would the table look for? Y equals 3x plus 7. Well, we put 0 in there, we get 7, and we get 10, and then we put and get 13. All right. Then, in trying to motivate the idea of what a slope means and what an intercept means, I say, okay, let's look at this over here. Every time we increase 1 unit, we typically increase our y 3 units, don't we? Do you think it's by accident that these two numbers turn out to be the same number? No, it's not by accident, because it is precisely the definition of the slope. As x increases 1 unit, the change in y is 3 units. That's what our slope is. That's the definition. Then I asked them, do you think it's by coincidence or by design that 7 just happens to be beside of x equals 0? No, it's because by design. That's precisely what the intercept is. It's the value of y when x is equal to 0. Now, transition that into b0 plus b1x, right? You think that helps us define our intercept and our slope? Well, absolutely it does. The intercept is the predicted y, so we're no longer looking at y's, we're looking at predicted y's. Of course, predicted y's aren't observed, so that's kind of confusing. But in the spirit of our regression model, the interpretation of our beta 0 is the predicted y when x is equal to 0. The interpretation of our b1, our slope, is as x increases 1 unit, our predicted y increases b1, b3 in this case, right? Well, that leads us into dummy variables. So if I am predicting, say a GPA from GRE, where GRE is quantitative, and I have a slope of maybe 0.15 for GRE. So I have my predicted as whatever my beta 0 is plus 0.15 times GRE. The interpretation of that is what? Well, as we increase GRE by 1 unit, the predicted GPA increases by 0.15 units. All right? So that's pretty easy to do. Now let's say that we're predicting GPA All right, so stay with me, guys. Now we're predicting GPA from gender. And again, I wouldn't do this. This is just for illustration purposes. If I was looking going to examine the relationship between gender and GPA, I'd run probably an unpooled 2-sample t-test, right? I wouldn't use a single predictor that's categorical dichotomous in this case. But just for the sake of the illustration, let's say we did that. And we could, right? So here, again, I've got my predicted value, I've got my beta 0, I've got my coefficient, and I have gender. So could I interpret this? Well, what does a 1 unit increase mean? Well, 1 unit increase means we're comparing females to males, right? We're increasing 1 unit. So whatever this is, this tells us that whoever's coded 1 scores 1.2 higher than whoever's coded 0. A 1 unit increase can even be interpreted when we have categorical data as long as it is dichotomous. But What if we're trying to predict GPA from school district and we have 5 school districts, A, B, C, D, E, for example? What's a 1 unit increase mean? Well, we don't know, right? A 1 unit increase isn't anything. We can't make these things zeros, 1, 2, 3, 4, and so on, or 1, 2, 3, 4, 5, whatever, because those are just placeholders. They don't take on a quantitative meaning. We're just using a number as a placeholder, as an assignment of a category. So because increasing 1 unit in the coefficient has absolutely no inherent meaning, at least no meaningful interpretation when we deal with categorical data. Now, because of that, what we have to do is we have to create dummy variables. So let K equal the number of levels. We're going to choose a base group. Of zeros and ones. Zeros not in that group, 1 is in that group. So I think I gave an illustration of the new matrix, so to speak, of zeros and ones in a previous lecture. So I'm going to go directly to the application of that. Now, let's say we use R just straightforward, and we just want to create a model here, and we want to predict first year college GPA from ACT plus the district. Now, before I hit enter, I'm going to tell you what's going to happen. It's going to select one of these. So it looks like to me over here on the spreadsheet, we have, A, B, C, D, I believe. I think there are 4 school districts. I believe there are a huge data set. I'm pretty sure. I'll tell you what, I want to confirm that before I... So yeah, we have 165 in A and 149 in B and so on. So I have 4 school districts. So now I want to create my model. Sorry about that. I just wanted to make sure. Now, let me tell you what's going to happen. Our output is going to have 4 predictors. Well, it's going to have 5 predictors. It's going to have 5 lines. It's going to have 1 line for the Intercept. It's going to have 1 line for the ACT. And then it's going to have 3 additional lines for the district. What's going to happen is you're going to see that one of these districts isn't going to be included because that's going to be our reference category. So the other 3 predictors, the dummy variables, are going to be a comparison to that predictor. So, well, that's fun. What did I... Oh, I did GPA is PGA. All right, whatever. Got PGA on the brain. Maybe I got some golf on the brain. It is almost time for the Masters, so cool. All right, so exactly what I said would happen. Notice that District A isn't included here. So District A is the reference category. So how do we interpret this line right here? Well, this line right here would be interpreted as controlling for ACT and District CA comparison and District D A comparison. Now, an increase of 1 unit tells us what? We're comparing from district B to A, right? So a negative tells me that district B is lower than our comparison group. So we would say the predicted first year GPA or first year PGA. I just do it like this. The predicted first year college GPA is 0.056 lower for district B than for district A. Now, a couple of nuances here. What if we want to compare District B with District C? Well, we can't do that with this analysis. We would have to run another analysis to make that happen. Now, and shifting the base group is easy. I can just recode district. And I can use the relevel. So I can just put district there. And I can put, what do we use there? I forget what we call that. I'm just having a complete brain freeze here. And I'm not even eating ice cream. Is it level? I'll tell you what, let me get some help on the relevel. This is kind of good it happened. So reference, that's what we need. So relevel, we have our vector, and then we have our reference, typically a string. All right. So district recode. We want district. Oh, shoot. Guys, there's something going on outside, and it's got me distracted, and it's not cool. So reference, okay. All right, I'm back with you now. I promise. District recode. Relevel. We want to district reference equal, and I don't know, let's just say we want this to be C. Whatever. Man, somebody's knocking at the door. Okay, I see what it was. It's a UPS guy. I was putting up a video earlier. My next door neighbor just walked right in, and I'm like, glad I wasn't sitting here in my underwear or something. So anyway, it's just too much going on for me to stay focused. Now, sorry about that. So if I want to go back up to the model, and instead of using district, you can probably hear my Arlo, my security system going off because of all that's going on out there. Okay. All right, so what you can see here is because we set the reference equal to C, then we have all of our comparisons to C. So this would be an A to C comparison. This is a B to C comparison. Of course, this is a D to C comparison. Interestingly, District C must be a high-performing district because all of these estimates are negative, indicating that the, controlling for the ACT, that the predicted first-year college GPA would be lower for A, lower for B, and lower for D. So I'm glad I lucked up and chose, even through all the clumsiness, that I chose reference C. I lucked out there. Now, how do we do all this in R, with matrix operations? in general? Well, the first thing we would need to do is set up our dummy variables. So what I'm going to do here is I'm going to establish, first of all, my reference. I'm going to just let C be the reference. All right? So D1 will be is A to C comparison. My dummy 2 is B to C comparison. And D3, of course, is D to C comparison. Now, I think this is doable in R, but I think it's a lot more complex than just taking care of it over in Excel. So what I'm going to do is I'm going to just sort my expand the selection with my districts, and using some just convenient fill down, it works nicely. So I need my first dummy variable, second dummy variable, my third dummy variable. So every place that I see an A to C comparison, since dummy 1 is the A to C comparison, when I see an A, I need a 1 in the D1, and I need zeros in the D3. Now, the beauty of it is all of my A's are going to be the same structure. All right, what do I want for B's? Well, it should be pretty obvious that I want my dummy 2, because the dummy 2 is B to C comparison. Again, I think this is the easiest way to do this. What will C be? Well, C is going to be all zeros, because we don't have a C to C comparison. Some people may say, well, this is an awful simple approach to, surely it's harder than this. One of the most commonly missed problems on exams and assignments in 5500 has historically been problems that have dealt with setting up dummy variables. Because what I'll do is I'll give you, on an exam, I'll give you a very small data set, 6 subjects maybe. And I'll have you set up the dummy variables in the design matrix, just by writing it out. Okay, so we have the dummy 1, dummy 2, dummy 3, dummy variables set up. So now I'm going to save this as something new. So I'm not very creative, so I'll save it at that. And now I'm pretty much set. So I need to, I'm just going to go back up and I don't know why all that's there. So I'm going to so I have ACT with CSV. So when it comes to following objects or masks, what that says, just tells you, is that these variables are kind of put on hold, if you will, because they were used in a data set that was previously attached. So typically, a red warning from R means we've done something wrong, but we haven't here. I just want to take a look at the new data, and you can see that we have our dummy variables now. Okay, now, as we should expect, transitioning into matrices, we're going to set up a Y matrix. So we went first year college PGA. In row, I don't know. Let me back up here. So we have we have a huge data set. So my Y is going to be matrix, first year college PGA. In row is 705. In column equal 1. By row equal false. All right, now we need to get our design matrix. So same game. Multiple ways to create your ones. This is the way I do it. There are other ways, obviously. So I need to C-bind some stuff. So I need my ones, I need my ACT, I need my D1, my D2, and I need my D3. Notice that I no longer use my district of A's, B's, and C's. Again, in matrix operations, that is completely irrelevant to us. In columns are going to always be equal to the number of things that we're estimating. So we have 5 there, right? Now the last thing I want to do is look at the X matrix, because it's going to be a 705 by 5 matrix, so it would just clutter up the desktop, or not the desktop, but the output, and I don't want to do that. All right, let's grab our B. So we know that. Look, there's something else I wanted to show you before I went into this, but well, let's just let this happen. So our beta should align with what we have before. And this works out nicely. It's where we don't have to even look at it, so we can see that our betas are the same. That's pretty good, because it'd be pretty goofy mathematics, matrix operations, if it gave us something different. Now, again, I can't emphasize this enough, and I think I've said it a lot. Once we get the operations down for simple linear regression, with just a few modifications, specifically to the design matrix, all the other calculations follow suit, right? For example, if I want the structure of my variances for my betas, they're called the variance covariance matrix for the our betas. Well, we know that we can do that with the mean square error. So I would create the I would just run the ANOVA of our model to get the mean square error. It's kind of cheating, right? But so it's 0.348. So the variance covariance for B is going to be the mean square error times the inverse x. So what do we have here? What's the first diagonal? That would be the variance of beta 0. This is the variance of beta 1, which in this case is ACT. This is the variance of our dummy variable 1. This is the variance of dummy variable 2, and this is the variance of dummy variable 3. You can see that our standard errors are very, very, very small, as demonstrated by our output. All right. Even though we're in a multiple regression perspective, we can still calculate our predicted values. And probably the easiest way to do this, we can use, remember, we can use our hat matrix, but we haven't calculated it yet. So the simplest way to get our predicted is just take the design matrix times our beta. And I'm not going to do y hat because, you know, we would have 705 elements there. Our errors, again, are easy to calculate. It's just our predicted, or I'm sorry, our observed minus our predicted. So our observed would be the first year college PGA minus our predicted, so just y hat. If we want to look at a histogram of our errors, again, is that a normal distribution? No, it's not a normal distribution. Don't say that. But it does look like this distribution, which is a sample of our errors, it's reasonable to think that this does come from a normal distribution. So the normality of our errors, I think, is reasonable. Now we could get a QQ plot, as I've demonstrated previously, but I'm not going to get into that because I think it's time to end this video. I can't think of anything else that I really wanted to calculate. Well, I'll tell you what. Let's do one more. Let's do the variance of our errors. If you already know how to do this, feel free to terminate the video, stop the video, and go on. So we know with the variance of the errors, the variance covariance matrix, we need the mean square error. We need the identity matrix. So the identity matrix here is going to be the diagonal. We need 705. And we need our hat matrix. So to create our hat matrix, we need X inverse Now our hat matrix is going to be huge. It's going to be 705 by 705, so we don't want to go there. So the variance covariance of our errors is going to be the mean square error times our I minus our H. Now it's going to be a huge, I hesitate to do this, but yeah, I don't even know it's going to print them all out. But, just to give you an example, yeah, that's why I don't like to do this, because it just overwhelms the output. Goodness gracious. Of course, 705 by 705 is, a huge matrix. Well, this is fun. Remind me never to choose a data set this large again. Not that you can remind me, because these are recorded way before you get them. Well, we having fun yet? All right, finally. All right, so what does this first entry give us? It gives us the variance of the residuals for the first case. What does this value give us? It gives us the covariance of the residuals for the first case and the second case. So, sorry about that, guys. That was just insane. I'm done.